Alright, let's go. Stellar black hole. Stellar black holes are the most common type in the universe, and they're born from one of the most violent events in existence. When a star, at least 20 times more massive than our sun, exhausts its nuclear fuel, the outward pressure holding it up vanishes and the core collapses inward in a fraction of a second. The resulting explosion, a supernova, blasts the outer layers of the star across space while the core crushes itself down into a singularity, a point of infinite density wrapped in an event horizon. For a black hole around 10 solar masses, that event horizon is only about 30 kilometers across, roughly the size of a city, yet its gravity is so extreme that not even light can escape. The first confirmed stellar black hole, Cygnus X1, was identified in 1971, about 6,000 light-years from Earth, and it's been slowly stripping gas from its companion star ever since, the stolen material spiraling inward in a superheated disk, glowing brilliantly in X-ray light. LIGO has since detected stellar black holes formed from mergers reaching up to around 142 solar masses, pushing the boundaries of what this category even means. They are quiet, dark, and scattered throughout every galaxy in the universe by the billions, most of them drifting invisibly through space, betrayed only when something wanders close enough to fall in. Supermassive black hole. Supermassive black holes occupy a completely different category of scale, the kind of scale that makes the word enormous feel inadequate. While a stellar black hole might weigh 10 times the sun, a supermassive black hole weighs millions or even billions of times as much, and one sits at the center of almost every large galaxy in the universe, including our own, Sagittarius. A star, the supermassive black hole at the center of the Milky Way, clocks in at around 4 million solar masses and sits approximately 26,000 light-years from Earth. Despite that distance, astronomers managed to image it directly in 2022 using the Event Horizon Telescope, a planet-spanning array of radio dishes working in coordination. The first black hole ever imaged was M87 star, captured in 2019, tipping the scales at an almost incomprehensible 6.5 billion solar masses, with an event horizon larger than our entire solar system. When supermassive black holes actively feed on surrounding gas, they become quasars, the brightest persistent objects in the observable universe, outshining entire galaxies of hundreds of billions of stars. One of the strangest facts about them is that their size actually works against the drama you might expect. The tidal forces at the event horizon of a truly massive one would be gentle enough that you could cross it without immediately being torn apart. You'd be doomed, just not immediately. How these giants formed in the first place remains one of the biggest open questions in astrophysics. Intermediate black hole. For decades, black holes came in two deeply unsatisfying sizes: stellar black holes topping out around 100 solar masses, and supermassive black holes starting in the millions. The enormous gap in between was conspicuously empty, like finding skyscrapers and garden sheds, but nothing in between. Intermediate black holes, with masses ranging from roughly 100 to 100,000 solar masses, are the missing link, and pinning them down has been one of the harder problems in modern astronomy. The strongest confirmed example came in 2020, when LIGO detected a gravitational wave signal called GW190521, produced by two black holes merging and leaving behind a remnant of approximately 142 solar masses, which sits firmly in intermediate territory. Beyond that, a strong candidate called HLX1, found lurking in the galaxy ESO 243-49, is estimated to carry around 20,000 solar masses based on its X-ray brightness. Though its classification remains debated, many astronomers believe intermediate black holes hide at the centers of globular clusters, those ancient dense balls of millions of stars, their presence betrayed by stars orbiting invisibly fast around what appears to be empty space. The leading theory is that they serve as the seeds that eventually grew, through mergers and feeding, into the supermassive monsters sitting at galactic centers today. Finding more of them would fill in the complete story of how black holes evolve across cosmic time. Primordial black hole. Primordial black holes are unique because they are the only type that requires no star, no explosion, and no collapse to form. Proposed by Stephen Hawking in 1971, the theory holds that in the first fractions of a second after the Big Bang, the universe was dense and chaotic enough that random fluctuations in energy could have compressed regions of matter directly into black holes before any star ever ignited, ever. Their potential mass range is extraordinary, spanning from objects near the Planck scale at around 10 to the negative 35 meters, which is almost unimaginably small, up to thousands of solar masses depending on when they form. At the tiny end, they would be subject to Hawking radiation, the slow quantum evaporation that causes black holes to lose mass over time, and a primordial black hole with a mass of roughly 1,000,000,000,000 kilograms would theoretically be finishing its evaporation right now, releasing a detectable burst of gamma rays. Some physicists have proposed that primordial black holes in certain mass ranges could account for a portion of dark matter, the invisible substance making up most of the universe's mass, though gravitational lensing surveys have ruled out many of those mass ranges as a dominant explanation. No primordial black hole has ever been confirmed to exist, but their potential detection remains one of the most exciting open frontiers in astrophysics and cosmology. Rotating black hole. Almost every black hole in nature is almost certainly a rotating black hole, because the stars that form them rotate, and conservation of angular momentum means that rotation only intensifies as they collapse. The mathematics describing them was worked out by Roy Kerr in 1963, and what he found was radically different from a simple static black hole. Rotation warps the geometry of space-time so dramatically that the singularity at the center is no longer a point but a ring, and surrounding the event horizon is an additional region called the ergosphere, where the spinning black hole drags space-time itself around with it so forcefully that nothing, not even light traveling in the opposite direction, can remain stationary. This effect, known as frame dragging, means that space near a rapidly spinning black hole is physically being swept around like water in a whirlpool. Roger Penrose showed in the 1960s that the ergosphere could theoretically be exploited as a power source. Objects entering it could extract rotational energy from the black hole itself, a process now called the Penrose process, which could in principle recover up to around 20.7% of the black hole's total mass energy. M87 star is estimated to be spinning at roughly 90% of the maximum physically possible rate. A maximally spinning black hole also has a significantly smaller event horizon than a non-spinning one of identical mass, compressing the point of no return down further. Kerr's solution is almost certainly the most physically accurate description of real black holes. Charged black hole. A charged black hole is, mathematically speaking, a beautifully complete object, and astrophysically speaking, almost certainly a fiction. The solution describing one was worked out independently by Hans Reissner in 1916 and Gunnar Nordstrom in 1918, making it one of the earliest exact solutions to Einstein's field equations. The physics allows for a black hole carrying a net electric charge, and the consequences are strange. Instead of one event horizon, a charged black hole has two, an outer horizon and an inner one called the Cauchy horizon. And at the Cauchy horizon, something deeply unsettling happens. Determinism itself breaks down, meaning the equations can no longer predict what happens next. The reason astronomers don't expect charged black holes to exist in practice is straightforward. Any black hole forming in a real environment would be instantly surrounded by plasma, ionized gas carrying particles of both charges, and it would immediately attract whichever charge it needed to neutralize itself. The process would happen so fast that maintaining significant charge is essentially impossible. Despite that, the Reissner-Nordstrom solution earns its place in physics because it revealed the internal structure of black holes in a way the simpler non-charged version couldn't, introducing the concept of multiple horizons and the Cauchy horizon that still feature in modern theoretical research. Rotating and charged black hole. The Kerr-Newman black hole, described by Roy Kerr and Ted Newman in 1965, is the most general single black hole solution that general relativity allows, combining both rotation and electric charge into one complete mathematical object. In practical terms, it's even less likely to exist in nature than a purely charged black hole, since the same plasma environment that neutralizes charge also exists around spinning black holes. But as a piece of mathematics, it is the final and complete picture. What makes the Kerr-Newman solution philosophically remarkable is that it encodes everything about a black hole in just three numbers: mass, angular momentum, and electric charge. No matter what fell in to create it, no matter whether it was made of rock or gas or exotic matter or entire civilizations worth of information, the black hole retains only those three values externally. This is the no-hair theorem, formalized through work by John Wheeler, Jacob Bekenstein, and others in the 1970s, and it means black holes are the most information-destroying objects in the universe. Every other type of black hole in this list is actually a special case of Kerr-Newman. Remove the charge and you get a Kerr black hole. Stop the spin and you get a Reissner-Nordstrom black hole. Remove both and you get the simplest solution of all, the Schwarzschild black hole. It is, in a sense, the final boss of black hole mathematics, naked singularity. A naked singularity is what you get when the mathematics of general relativity produces a point of infinite density without wrapping it in an event horizon, and it is the most disturbing theoretical object in physics. In every known black hole, the singularity, the region where density becomes infinite and the known laws of physics break down completely, is hidden behind the event horizon, shielded from the rest of the universe. Roger Penrose proposed in 1969 that this is not a coincidence but a fundamental rule of nature, which he called the cosmic censorship conjecture. Nature prohibits naked singularities because exposing them to the outside universe would allow signals from a region where physics itself fails to actually reach observers, making the universe fundamentally unpredictable. The problem is that Penrose's conjecture has never been mathematically proven in full generality. Certain theoretical scenarios, such as spinning or charging a black hole beyond its mathematical maximum, would cause the event horizons to shrink and merge and then vanish, leaving the ring's singularity bare and visible. Some numerical simulations run under very specific fine-tuned conditions have produced naked singularities, though physicists generally argue these are mathematical artifacts, rather than physical realities. If one ever did exist, an outside observer could theoretically receive information from a region where the laws of physics, as we understand them, have completely collapsed, meaning that the universe would contain a point from which all predictability radiates outward. Most physicists believe nature finds a way to prevent this. Nobody has proven it. If you want to see more, click the video on screen now.